If you're length matching your differential pairs down to 1/1000th of an inch, down to those mils, but you're still getting issues in your eye diagram, EMC testing, and your receiver pins are still throwing errors, well, length matching may not be sufficient. There are at least 5 more things that could be causing problems for your differential pair. Hello everyone, I'm Kirsch Mackey, an electrical and electronics engineering consultant. And in this video, I'll be covering the top 5 things that could be causing problems for your differential pairs. So starting with problem number 5, tight coupling can be working against you in fabrication. Tight coupling means very narrow traces and tight gaps. Your fabricator's etch tolerance becomes a larger part of your trace geometry. That could cause your impedance to shift away from your designed value. And with issues in fabrication, you'll get reduced yield and more scrap. This can cost you millions of dollars, depending on how many units you're selling per year. So what's the fix? The fix is to pick a PCB stack up and set of trace widths and tolerances that your fabricator can actually handle. When it comes to differential pairs, closer is not always better. Controlled is better. Now that's problem number 5. Number 4 is the problem that catches almost everyone. So problem number 4 is whenever you make a change in your reference plane, that can break the EMC balance in your differential pair. When your differential pair transitions between layers, your return current needs to make that change in reference too. Without a nearby return via, the electromagnetic field spreads among the PCB as well. That spreading produces coupling, EMI, and common mode noise. So what is the fix? The fix is to place a return via at every layer transition and make sure the reference plane or the return conductive material structure stays continuous from your transmitter to your receiver, even through the PCB layer transitions. Problem number 3, the way you correct your bend creates its own discontinuity. The serpentine patterns and the trombones that you add to differential pairs in and of themselves can introduce their own impedance discontinuities, including phase mismatching for dynamic phase of your differential signals. See, every bend that you add adds local inductance and also capacitance, and too much bend correction creates coupling and common mode noise. The fix is to use the minimum amount of geometry to match the length between the diff pairs. And for dynamic phase alignment, which is different from length matching, you want to place the correction as close as possible to the source of the mismatch. Don't place the correction at some arbitrary point down at the end of the route or based on generic rules. Okay, we're almost there. We're at problem number 2. Vias can create imbalance in your differential pairs. So every layer transition introduces a via, obviously, but there are multiple things that can change your impedances and capacitance. There's antipad size, the drill diameter of the via, and placing your vias asymmetrically. That can cause a mismatch between the diff pair. Also very important, depending on your rise times, missing that return via will create problems for EMC and therefore signal integrity, cause radiation, and also noise and ringing. Length matching the traces doesn't do anything to fix any of that. So what's the fix? The fix is, of course, to keep your differential pairs symmetrical, size your antipads against your impedance target, and place a return via or more at every layer transition. 2 is better than 1, but if you can only get 1, put it equidistant between the 2 differential pair vias, somewhere within the middle, in front or behind them. And this is problem number 1. Equal copper length doesn't mean equal electrical environment. 2 traces with the same physical length can have their signals still arrive at different times at the receiver. The signal delay depends on the entire electrical environment. It depends on the routing layer, the component pin parasitics, and it depends on the coupling between your pair and nearby traces. So matching copper does not mean matching signal arrival. So what's the fix for this? The fix is to treat length matching as necessary but not sufficient. You need to verify your signal delay at the pin and not just at the traces. Usually you want to do this using simulation, especially for complex PCBs. So the key takeaway here is that length matching is only a tool, it is not a guarantee of differential pair performance. The differential pair has to be balanced through the entire signal environment from the transmitter to the receiver. So match the lengths, but check the other 5 issues I covered in this video for your differential pair. I'll catch you in the next video.